Hi, thank you guys. So my name is Hee-sung. I'm gonna talk about a new broker load balancer available in Pulsar 3.0. And I'm gonna talk about some design details and then why we need it, and then some performance data and to share. Just a little bit about myself. I'm a platform engineer, Stream Native. Previously, I worked for AWS, and then today's agenda is pretty, like I said, pretty simple. First, we're going to talk about why we need load balancer in the streaming context, and how the Pulsar balances its load, and we're going to jump into the new load balancer designs and some obstacles we overcome, and the matrices, observability improvement, and test result, and future work, and Q&A. So why we need load balancer? That's a sort of like a big question. If you imagine your life without load balancer, it's going to be pretty terrible. You can cause waste of your invaluable hardware resources, of course, and then it can, more importantly, it can cause hotspots. You can increase your latencies, brokers, start restarting, and then killed. The latency will be, availability will be impacted, on all the bad things can happen. So, to resolve those issues, we usually relying on more manual work, such as topic repartition and topic reassignment. And also we need to configure other things like back pressure and then noisy neighbor isolation. So basically that means a lot of operation and on-call page will be also increased. So what is load balancing actually in our context, messaging and streaming context? In general, I think it means just balancing message loads to different brokers. However, in Pulsar, actually, it's quite different because of the compute and storage layer separation. So if you have to think about how we balance the load at the two different layers. So it's the broker layer, the first layer, the serving layer. Basically, we want to balance the topic sessions to different brokers. And at the storage layer, we want to distribute ledgers to different bookies. And then for those of you not very familiar with Pulsar, topics are segmented to different ledgers. The ledger is basically the unit of to store the messages into the bookies. So is that easy? So we understand that now load balance is important in streaming and then messaging systems. So is it easy to add it in the distributing messaging system or streaming system? In the monolithic systems like Kafka, I don't think it's very easy because topics are sticky to the disks. Topics are sticky to brokers, which means partition reassignment. So some operations like some load balancing operations like topic reassignments requires moving data across brokers, which is expensive. And which also requires a careful admin operations. That means the cluster can be degraded during this operation, and then the availability of the cluster might be impacted. Then what about Pulsar? Is it easy to add load balancing at Pulsar? I think yes, because again, thanks to the compute and storage separation. At the broker layer, we know that no messages are persisted in the broker servers. So we can just transfer the topic sessions to different brokers. So we don't need any message copies there. At the bookie layer, when you want to distribute the messages, or we can just create a new topic segment or ledgers, and then distribute to the different brokers. Different bookies. So for example, let's imagine we have a really busy topic, which has a lot of traffic, and we can just create a bunch of ledgers and distribute to the different bookies. So in the worst case, we can fully utilize a bookie cluster for that really busy topic. Okay, so in short, that means Pulsar load balancer involves no message move, no manual operation or admin operations. We do the load balancing on demand or automatic. It just causes some minimal topic unavailability while the client reconnects. And also it causes some message cache miss on the new assigned brokers, but that's just initial cache miss there. Okay, then let's talk about what kind of features, load balancing features are available in the Pulsar broker load balancer. Before that, we need to talk about the topic bundling because, in fact, Pulsar groups the topics into the bundles, and actually the bundle is the load balance assignment unit. So the reason why we are doing this bundling is to increase the scalability of the Pulsar. Tracking individual topic can be very expensive. So we want to group them and then upload together. That can reduce some overhead from topic metadata. So having said that, with this bundle concept, we can think of like three major load balancing features. The first one is bundle broker assignment. Second one is the bundle unload. Third one is bundle split. So about the bundle broker assignment, let's say a bundle or topic is not assigned by any broker. Then we need to assign a new broker to that bundle or topic so that all the topics belonging to that bundle can be served by that broker. So this happens on-demand fashion. So whenever the topic lookup happens or the producer is created, as consumer is starting consuming, when this thing happens, we need to identify which topic owner is there right now. If not, then we need to assign the owner. Bundle unload is very straightforward. Let's say some of the brokers are overloaded, then we want to unload some of the bundles from that overloaded broker to the less loaded broker so that it can be balanced. Lastly, we have split. Let's say this bundle is heavily overloaded, have a lot of traffic from many topics. You want to split it into two bundles, and then each bundle, smaller pieces of the bundle can be sort of unloaded to other brokers so that the unload can happen. Load balance can happen. So these are the three major load balance features available right now. Okay, so far we talked about the broker load balancer features and why we need a load balancer. Then why we need why do we need a load balancer, right? So over time, the existing load balancer has proven to work relatively well. But also it has some problems. It has some problems, and then I'm going to talk about some of the problems. I think the first problem is it was invented in 2017 first, and then over time, I think the community added a lot of features in the broker load balancer, and also added a lot of code to cover the edge cases. So I think the code needs a little bit of more cleanups. So that's the first item. I think we need more maintainable, and then we need to clean up. And the second item is very important. I think one of the important goals of the Pulsar is we want to make the Pulsar is less zookeeper dependent. Unfortunately, broker load balancer uses metadata or zookeeper for each load data and the ownership data. So it can be a really problem when you scale the broker cluster. Third thing is, we want to also optimize further the load balance processes. Like we want to improve the client reconnection delay, and we want to decrease the ownership conflicts, and then more distributed load balance decisions. And also we want to improve the existing the load balance algorithms and better observabilities. So let's step back, and as you can see, the second item, less zookeeper dependency, is the biggest architectural change. And let me talk about how we actually solve this problem. So we are actually going to use topic and table view to replace zookeeper dependency here. We're going to use, for the load data and then the ownership data, these are two major data sets for the load balancer. For load data, we have broker load data and then bundle load data. Basically, broker load data is CPU and memory and network usage, right? And bundle load data is how much traffic the bundle has right now. So with these two kind of data, we can identify which broker is right now heavily loaded and which bundle we want to unload first. So these are two sort of major load data for the load balance decisions. And then ownership data is also important because we need to discover the owner broker of the bundle or topic. So these two data need to be stored somewhere and then to be available for the cluster. For these two data, again, like we decided to use topic and table view, which are the native Pulsar components, and we believe that we can totally replace zookeeper with this native component, Pulsar components. Let's dive into more about the broker load data first. As I said, broker load data is basically CPU and memory usage, and it needs to be up to date, as up to date as possible. So we want to probably update it as frequently as possible. But if it's too much, the cluster can be too chatty. And so by default, actually, we compute the load score every 5 seconds, and then periodically broadcast to all other brokers. So individual broker actually broadcast this broker load data to other brokers periodically, with some exceptions if the load change is bigger than 10% or the last report is 15 minutes ago. These are all configurable, but I'm talking about the default settings. And of course, we want to reset the load score when the load balance event happens, like unloading happens, then we want to reset that the load data as well. About the load score, we're using exponential moving average to smooth any load signal spikes. Because if the CPU has so much spike, it doesn't make sense to use raw data, raw CPU signals for load balance decisions. Next, about the bundle load data. Like I mentioned, the bundle load data is just how much traffic the bundle has right now, and it also needs to be up to date. The problem is for the larger cluster, the number of bundles can be very large. So, or sharing the bundle load data to all other brokers or other brokers can be very chatty, and then the data can be pretty large. So for this problem, we decided to report only top K bundles. And then by default, we report only top K bundles. So periodically, from each broker, report only top K bundles load reports to the leader broker. And we also reset that the bundle load when there are some load balance event that broker is involved. The last one, the bundle ownership data, is to repeat. The bundle is the load balance unit, and then topics are grouped into bundles. And this is used for the broker discovery. You need to look up which broker is serving that topic or bundle. Previously, the existing load balancer, this bundle ownership data is persisted in zookeeper as ephemeral on C node, and then cached to all brokers for the performance reasons. And then if you think about it, this actually has some classical distributed system problems. We're now trying to copy the data to all different brokers, the ownership data, and then it needs to be consistent. Each copy needs to be consistent. If you're using cache, the cache should be coherent whenever updating happens from one node. And then if there is any conflict, you need to resolve the conflict. You need to also do some compaction if a new broker joins. You don't need to replay every messages from the day one. And also it needs to be fault tolerant. So next slide, I'm going to talk about how we actually overcome these problems using Pulsar native component, such as topics and tables, views, and compaction, topic compaction. Okay. First, we need to design the bundle life cycles first, because we have three major, basically, bundle events. If you think about it, we have assign and transfer or unload or split. So from the init state, we actually, if each bundle basically state follows some transitions, and then we need to formulate this state clearly so that we can identify any conflict scenarios. And then we can define the causality, what event happened before. Then then each broker then basically play its role in its transition protocol to clearly finish that the bundle state change event. Also for this in-flight states, we can also defer the client to lookups, which means we don't need to immediately return the client to lookup request. We can defer the client request in this if the bundle state is in flight, which means we can, when there are a large number of lookup requests to the cluster, we can reduce the broker's overload, which is thundering herd impact. We can this client to lookup differing can help in that situation. Then this bundle state change events. Now those events messages are published to a single topic. And then, because we're using a single topic, this can form a single linearized view of a bundle state changes to every broker, and then just brokers react on them. And then this component like topic, and then the event streaming, and then the actors, which means the brokers, and then the protocol over that the topic and the state life cycles, we call them as a bundle state channel as a single component here. So with this bundle state channel defined, like I said, we can kind of get a single linearized view, and then table views basically guarantees the ordered consumption of the messages. That means, and also the topic is persistent. It guarantees the sequence of the messages in a single order, so that we can guarantee the order, the sequential consistency, just like Jupyter. So we can actually solve this consistent problem with these solutions we just talked about. Basically, this is eventual consistency with some order. Also, we can resolve the conflict by version ID and state transition checks. So each message has a version ID, and then we can also verify the state change is valid in the state diagram. For example, let's say two brokers are trying to assign different owner brokers for the same bundle. We can check this version ID and state transitions, and then select which one is the winner. Like I mentioned, we can also use topic compaction and then compact these state change messages, so that when a new broker joins, it doesn't need to play the bundle ownership data messages from the day one. It can just take the last snapshot of the topic, and then replay from the last snapshot. And also the fault tolerance is guaranteed by the topic property itself, because we are using a ledger replication in the bookie layer, so it is fault tolerant. And also we have the bundle state channel leader monitor, So whenever a single broker or whenever some brokers are available, it gets notification from the leaders, so membership service. We can fix any orphan bundles from the cluster and then reassign the ownership. Next slide, I'm going to talk about some worst case scenarios. And then I'm going to explain how the Pulsar or the bundle state channel can solve them using the Pulsar properties. So the first one is, what if some of the brokers are slow? So what if some of the table views are slow? For example, we have two brokers, a slow broker and a fast broker. Let's say slow broker thinks the bundle is owned by the fast broker, and the fast broker thinks the bundle is owned by the slow broker. We have a circle here, right? So that the lookup request will be basically, make a redirection loop, and then lookup will eventually time out in this case. So for this problem, we are relying on the message delivery property of Pulsar. So we know that table views under the hood uses consumers, and we know that consumers eventually get messages eventually. So we know that because of the delivery property, Pulsar delivery property, we know that eventually the slow brokers table view should catch up and then solve these cycles, break these cycles. Next one is also similar. What if some brokers are slow? But in this case, each one thinks that they are the owner. So broker A is owned by, slow broker thinks that bundle A is owned by itself, and then fast broker thinks it's the owner now. So in this case, we can rely on the bookkeeper fencing here. Bookkeeper fencing means bookkeeper sort of guarantees there should be only one writer at a time. So one of the brokers, either slow or fast, they will fail to write messages to any to the ledger, and then see these ledger errors. And then, like I said, we also have this the eventual consistent property from the message delivery. So the slow broker will eventually catch up, and then it should get solved soon. Third case is also interesting. What if some brokers are suddenly unavailable? Let's say deployment happens, and then just got killed somehow. Then what happens? In this case, the leader broker gets notification from the membership service. Membership service is based on the metadata layer, Jupyter. And it can immediately schedule the ownership reassignment for the orphan bundles within some delay. The delay varies depending on the stability of the metadata store. But basically, within the delay, that broker that was unavailable came back, then the scheduled job can be canceled, and the ownership will remain to that old broker. If not, the new ownership will be assigned to others. And then leader broker also periodically checked any stuck in-flight states and any unavailable broker, and they will try to fix them periodically. The last case is interesting as well. What if the metadata store is unavailable? What if the Jupyter is gone? This is a disaster case. I don't think anybody wants to see it managing Pulsar. So this is a panic situation, and we will see many metadata connection errors, Jupyter errors, from brokers and bookies everywhere. And in this case, we don't want to add any more complexities in the system, so no orphan ownership fix will happen. And the existing topics will work as is, and then whatever the serving is just best effort basis. So we should just fix the Jupyter again. Okay. So far I talked about the bundle state channel and then edge cases, and then let's switch our gear to what new unloading strategy is available in the new broker load balancer. So we added this new unloading strategy, transfer shader. As the name hints, it actually pre-assigns, as the name hints, it actually unloads bundles from the overloaded brokers to underloaded. But the one different thing is it actually pre-assigns the destination brokers at the the unload decision time, not the assignment decision time. That's the big difference. And it utilizes the bundle state channel bundle transfer protocol. So it will follow basically this state changes like owned, releasing to assigning to back to the owned to the destination broker. The selection logic is simple. It just tries to transfer load from highest load to the low load brokers one by one. Second highest to the second lowest. And the trigger condition is also simple. I think it's simpler. It's just trying to make the global load distribution lower the target. The global load distribution here means a standard deviation of the load score. Or if there are any brokers significantly underloaded and overloaded. Let me give you some examples how it works. Okay, the box means the broker. So we have 5 brokers here. The number inside the box is the load score right now. So the first broker is pretty overloaded, like 90% resource usage is there. Here in this distribution, the average score is 50, and then standard deviation is 30. Let's say our target standard deviation is 25. And because the current standard deviation is bigger than the target, the threshold shadow will try some unloading procedure. As I mentioned, we will try to unload the bundle load to the minimum load broker to make the source and destination brokers load equal in the end. So after we unload 40 load from the first broker to the last load, in the end, the broker load will be the same. Similarly for the second and then the fourth broker. So after the unloading, one iteration, the average will stay the same, but standard deviation of the load score will be much less than our target. So the further unloading will not happen. The next one is some sort of like an edge case where we're trying to prevent infinite unloading. In this example, let's say we have 3 only brokers, but each broker has only one bundle and one topic inside. Then as you can see, we can now unload only 25% load from the single bundle. So in this case, the transfer shader will give up and it will not unload any, even if the current standard deviation is bigger than the target. So in this case, actually, we should ask the user to repartition the topics more so that each broker can have more bundles, or the bundle can have more topics inside, so that for the splits. Let's talk about what metrics are added in the new load balancer. In the existing load balancer, it only has, about the resource usage metrics, it only has the original resource signals for CPU and memory in the network, but it doesn't really have the computed score that are actually used for the strategy. So we decided to add those computed score, the resource usage score. And then the second one is max EMA, the max of exponential moving average, is the actual load score used for the threshold shader. Transfer shader. And we also added the global stats of the load score, such as average and standard deviation, so that you can plot these 2 load scores together with your target and monitor where your global load is ongoing, and then the load score as well. Next set of metrics is load balance sort of decision metric. For now, we only emit the success case metrics and the total count, but we want to add some breakdowns in the reason code. so that it can be more explainable when you plot them. So sometimes, load balance transfer, they think that we need to skip the load balance decisions. Then probably people need to just, curious about why it got skipped and so forth, right? For this case, we wanted to have some other skip or failure metrics with some region code. One thing I want to mention is the region code is quite limited, the list itself, so it's always better to check the decision logs. And for this decision log checking, we introduced this log balancer debug mode. So when you turn on, by the way, this is dynamic config. You don't need to restart the broker to turn on this flag. So when you turn on this flag, it will print more load balance decision log, and then you can debug why the load balance decisions happen such way. And then once your debugging is done, you can turn it off. Lastly, we have another set of metrics for bundle state channel. And this one is actually to check the sanity of bundle state. This is for checking how many there were how many open bundles or how many brokers are available and how many messages published, event messages published and consumed. So such information can be also available in this metric set. Okay, next, we did also performance tests, and we did 4 kind of performance tests: assignment scalability test, and assignment latency test, and unload test, and split test. So the scalability test is basically we want to see how quickly the client can reconnect when a large cluster shut down in a short amount of time. So for this simulation, we had like 100K publisher, 100K topics distributed to 65K bundles. And we kind of saw that like it was like 2x better performance. For the unloading test, basically means, unloading test means we try to see how quickly you can unload when the broker is scaled up and down. Just to sum up, so why is it better? I think this is because the data path, the data load balance data report is faster now. We are now using in-memory topics instead of zookeeper, so we don't need to go through the disk copies. And also there are less data to share. We only select the top key bundles instead of all. And we also have distributed load balance decisions. So the local brokers can now trigger the splits and assignment itself. So there is no like leader broker bottlenecks for the load balance decisions. And also faster orphan topic reassignment. We have a reader monitor that fixes all the orphan ownerships. And we also improve the sharing algorithm, which is the transfer schedule will reduce the number of unloading count. So I think with this improvement, we see some performance gains. So all I said is available online. So you can find those in one of our blogs. And then the Pulsar community did a really good job in the last year to update our Pulsar documentation. So please check that out. And lastly, we have a future work. We are trying to further optimize the client reconnection time without the lookups. So after this, we can see the faster reconnection time during unloading as well. Okay, so any questions so far?